A little quest. Okay, so our fifth lab. We're going to study mirrors, and I'm just going to scroll down and open up the simulation. So let's do that, and now we can see. I'm going to move this over a little bit. We can see better. This red arrow is the object, and so we can see these rays coming from the object, and they're hitting the mirror. The mirror is hidden behind this orange bar. So we're not really told any details about this mirror. Like, is it convex or concave? What's its focal length? So it's kind of intentionally hidden. But all we can see is the rays coming from it, and we can see quite a few of them. Three of them are special. We've got this red, blue, and green rays, which are colored. And these aren't exactly the three special rays that we draw. We learn about the ray diagrams. In particular, this blue one, that hits like the center of the mirror, where like the mirror and the principal axis meet up. So, if you have a spherical mirror, then at that point where it hits, it would act just like a flat mirror. So these angles here above and below the principal axis are the same. And we can move the object around, and we can see the image moves around as well. And our main goal, anyways, is going to be to find the focal length of this mirror. We also want to determine what type, like convex or concave. And so we're going to do this in two ways. One is by just playing around with this picture and looking at these ray diagrams. So if you move this point around, look at the ray diagrams, in particular, some of these special ones that are colored. And I won't tell you how to do it, but just try to figure out what the focal length is from, moving this around. And you should be able to figure out just by looking at these numbers here. And, like once you move the object to the right place. So I won't say any more about that. That's your goal, is to figure that out. And that's the focal length for part A. Now for part B, we're going to look at the equation. Actually, let me bring that up. Let's write down our equation here. So 1 over dO plus 1 over di equals 1 over f. So we know that equation applies to this mirror. I should say, I'm telling you it applies to this mirror. It doesn't apply to all mirrors, but for a spherical mirror, which is what we have. So, what we would like to do then is collect data. And if you look at the object distance, we can move that around from 200, looks like in 1 centimeter increments, all the way to 5 centimeters from the mirror. So we could get quite a lot of data from this. We're just going to get 20 points of data. So you want to make a table. I'm going to do this, where we have DO, which you pick. So that's the independent variable. And then DI. So initially, we'll put DO as 200. And, should have left room for this, but you can see from the simulation that these are measured in centimeters. So at 200, the object distance is 200, the image distance is 100.75. So we would write that here. And then we're going to go in 10 centimeter increments. So you go 190, 180. And again, if you have like just like one screen that you're working with, it's probably best to actually do this on paper. Just make the table. You can fill out this column here for DO, and then just go to the simulation and fill in the numbers. So we go to like 190. Now, it's sometimes actually hard to get it. Maybe it'll be like 189 or 191. And if that happens, big deal. Just, record the value accurately. But if you want to do like, say, say 190, 103.5, we go to 180. Let's say you have trouble zooming into 180, and you decide 181. That's fine. Then you just change this value to 181. And write down the image distance here, which is 106.38. So again, they give us a lot of significant figures here. So you can imagine that this lab is going to work out fairly well, probably better than a real experiment would. And yeah, you go all the way down to 10 centimeters. And I'm actually going to do that point. Let's zoom in 10 centimeters. Had it and lost. There we go, 10 centimeters. And the image distance here is minus 11.75 because it ends up on the other side of the mirror. And so you'd want to put that in there. It was 11.75. So yeah, if you're on the other side of the mirror, enter your numbers as, your values as negative numbers. So you're going to make this table, and then that's part of the lab. So if we go back to the actual lab, I'm going to adjust this after recording the video, but yeah, we've got all this stuff here. There's a few questions, but then, yeah, now we're on part B. So we collect all this data, and then we're going to make a table using a spreadsheet, and then you just take a screenshot of that. Of course, give it a name like table 1, and give it a, describe what this table is. And just get a screenshot so you can turn it into like an image or a PDF and upload that. And if we go back to our equation, the data we're collecting is DO and DI. And the relation between these two variables is very clearly not linear. And so we want to linearize the data by making substitutions. So we're going to say x equals and y equals. And again, your job is to figure that out. Like, if you can't see it, just try kind of guessing. Now, there are a couple valid ways of doing it. But remember, what we're doing is we're fixing the object distance. So that's our independent variable. So x should probably have something to do with DO. Might be DO, it might be something related to that, but it would work if you did it the other way. If you let x equal something related to DI. But that's the idea. And again, this part is something students struggle with quite a bit in this class. But it's really one of those things everybody should get right, because if you do it wrong, it should be kind of obvious. So I'm going to give you an example. Let's say x equals DO. I'm going to do it wrong. And let's say y is 1 over DI. Calling it, say, x equals DO and y equals DI, that accomplishes literally nothing. You're just changing, you're not really changing the mathematical form of it. You're just changing the letters. Nothing good's going to come out of that. So at least we've done something here. And let's check to see if that's right. So 1 over DO, we have 1 over x. Then we have plus 1 over DI. Well, 1 over DI, that's equal to y. And that's equal to 1 over f. Just to emphasize, I'm going to call that c, because it is a constant. And so that's the first step. Once you make your choice, for the substitutions like x equals and y equals, then plug them into the main equation, this one. And then you have this equation here, and to see if it's linear, just solve for y. So we'd have y equals minus 1 over x plus c if we solve for y. Now, our equation should equal, if we did it right and linearized it, what we should get is y is equal to some constant times x plus another constant. Like y equals mx plus b, where m and b are constant. And so clearly this did not work because we have x in the denominator. So I saved you a little time on this. Don't make this substitution here. So try something else and then plug it in to your main equation and solve for y. And just make sure you have a constant times x plus another constant. Now, a lot of times this constant here will be 0. I'll give you a hint. In this case, it's actually not going to be 0. And so now we've linearized our data once we get the right substitutions. And so then what we're going to do is make a new table. We're going to have a table. Actually, I can draw better lines using this. It really matters, but include units everywhere. And so now we'll make our new table x and y. So again, you'll have these numbers. And again, you'll have them in a spreadsheet. So instead of doing like 1 over 200 on a calculator, where you get like 0.005, and then like 1 over 90, you don't do each one of these individually. Here, let me, I'll put in a few values. Let's just say we have 4 data points. So I've got 200, 190, 181, and 170. I know you can't see it right now, but I'm going to type all the values in first. So let's go back to here. 190, 103.5, and 170. So I only have 4 data points. That's 110.58. So this would be like DO, DI. And I should, these are in centimeters. And then we're going to make a new table of x and y. Now, let's say I screwed up, and I'm going to use the same substitutions as before. So x is equal to DO. So what I would do is say x equals DO, and just drag this down. And then y was 1 over DI. So if I do 1 over DI, get that. And so now I'm going to plot this data, and we should see it's not linear. So that's another clue that you did that wrong. Let's insert a chart. We can just do x, y, scatter. And then here you can put in title and the axes, but it actually does look linear, even though it's, if we collected all the data, then this one would not be linear. So actually, that's a good reason to check algebraically to see if your data is linear, because this would definitely look like it was linear. I'm going to look at the r squared value. It's just because we have so little data. Yeah, r squared is pretty high. Okay, and this is a little more, I guess, with only 4 data points. I mean, if you have any 2 data points, that's perfectly linear. And so just adding a few more Yeah, we should have, or I should have made more of a table here before doing this. But yeah, with more data, we would have seen that this is not linear. And then what we would want to do is record the slope and intercept. So again, I think it just looked horrible on the graph. So what I would do is I would write these values down and then delete it. You can leave them there if you like. And of course, every time you make a figure, you want to have the axes labeled X and Y along with the units. And yeah, then you've got your slope and intercept, which also typically have units. In this case, the slope, like if we were to plot just this DO and DI, they're both in centimeters. So if we plotted, like, say, DI as a function of DO, when you take the slope, you're going to be dividing a centimeter by a centimeter. That would just be a number. Depending on your substitutions, that could be the case here as well after you've linearized your data. And yeah, so again, just do the best fit line and write down the values. And yeah, so you don't need it on your graph. Like you'll see after this, here's where you make your substitutions. So you just write x equals whatever, and submit that. And yeah, like here, it's what is the slope, and here, what is the intercept, and then you'll use that data to find the focal length. I should call that focal length of the mirror. I'll have to fix that. And then, or in part A, using just those special rays, the colored ones, we found the focal length of the mirror. And now we're doing it by collecting data and using the best fit line. So we'll make a table comparing them. So that table, I can make room on here. The table, you'll have like focal length from part A, along with units, focal length from part B, and then you'll have the percent, and you have to pick one. You want an error or difference. And she'll have a table that looks something like this, which of course you want to give like a name and a description of what this table is. And yeah, that'll be it for this lab. And keep in mind that this is a simulation. And so your errors should be like the difference between these two. When you plot your data, it should look very linear. I know in this example, well, I'm actually going to do it using my data that I collected for the entire 20 data points. I'm going to try to linearize it the way I did here and just see how non-linear it is. But I'll just do that later. But yeah, with more data points, yeah, with only 4, yes, it's not terribly surprising that it came out somewhat linear. Yeah, basically that's the last thing you want to do then is upload this table. So again, always give a name and a description of any table. Like in this case, it would be table 2 or table 3. Like we had this here where this is table 1 here. I guess you could call this table 2, but you don't need to upload it because you already told me what substitutions you made. So just to do, it's kind of unnecessary to do this because I'll see all your data, like what substitutions you made and the actual plot. So yeah, you can call this table 2, and then this one would be table 3, and just give it some kind of a name, and then that'll be it for this lab. All right, so yeah, I'm going to make a few changes to this, but then that should be good.